Well, now we have all the tools we need. We learned differentiation, integration, and important theorems of the vector calculus, and we are going to put them into practice. Let's use what we learned to verify the Green's theorem for a particular case. Let's say that we're given that vector field, and we're given a region A with the area A bounded by these curves so that it looks like that. So there's a curve 1, curve 2 and curve 3, so we have a triangle, and that is the area. So we want to show that integrating over the area is the same as integrating over the boundary if we do it in the right way. So let's demonstrate that this works. So first we just write the components of our vector field, which is the y and 2xy. And then we integrate over the curve S1 along that curve first. So that curve has y equals 0 because it's parallel to x-axis, and therefore both components of the force is 0. So the integral is just 0, nothing to compute, which is nice. What about the second curve, if we integrate along that curve? Well, this time we move along x equals 1, so we move vertically. And then f1 is y, because it does not depend on x. And the second component is 2y, so we'll substitute x equals 1 here. And since x is constant, dx does not change, but dy does. So all we need to do is just to compute that integral, which we do to get 1. Fine. What about the last curve? Well, this time we integrate along a straight line, so let's just make a little sketch. So I have a line moving from that point to that point across a straight line. So that is our C3. And we know that actually x changes from 1 to 0, because that's where we start and that's where we finish. So that's important. Always pay attention to the limits, where you start and where you go, because otherwise the sign of the integral will change. So we do that, and we know that this is just line y equals x, so the first component is x, second is 2x squared, and as I said, we move from 1 to 0, and because we had that straight line, we can also say that dx equals to dy, and our integral, which is f1 dx plus f2 dy, becomes an integral from 1 to 0 x dx plus 2x squared dx. So again, this is the same because the line is just x equals y, so we differentiate left and right of that. And we substitute inside, instead of the abstract f1 and f2, we get the actual values. Which brings us to integral from 1 to 0, x plus 2x squared dx, which is just in algebraic expression 1/2 x squared plus 2/3 x cubed. But note again the order of the limits. So first is 1 and then is 0, which makes it a negative -7/6. So that is the answer to the final bit of our integration. So we completed the integration over that curve now. So we have that integral. We just need to put it together, so we can split an integral over this curve as the sum of three integrals taken in the correct directions. So if we do that, we'll see that the total answer will be -1/6. Okay? Well, now let's compare it to the right-hand side, to the integral over the area, the surface integral. So that's how we need to use it. That's a definition, part of the Green's theorem. And if we differentiate our field, so just a reminder, f1 is x and f2 is, f1 is y and f2 is 2xy. So if we differentiate it, we get 2y there and just 1 there, okay? And then all we need to do is to compute the double integral using the way we've been taught previously. And if we do it by computing the y integral first, because it's known, we can get -1/6. So that's what we wanted. So the left-hand side of the Green's theorem is the same as the right-hand side, which we will require to demonstrate.